Despite being the person standing. But our speaker today is Chandrima Kayal. She is a postdoc at IMSC and she joined IMSC in October, I think, with Meena Majan, is that correct? And before that, she was a PhD student at Saurabh Chakrabarti. So I'm very happy to have her here, and she'll talk about the composition of randomized query complexity and approximate degree.
Thank you for having me here. So let's start. Okay, so today we'll be talking about mostly Boolean functions only and model of computation that around which we'll be talking around, that is query model, which I will introduce shortly. Now, depending upon model of computation, there are various complexity measures that generates there, and there are various complexity measure that is not directly the query complexity measure, but it relates nicely in the query world, and we can relate nicely when we talk about such complexity measures also. For example, like I will define them when we will read them. So there is like one example I wrote there, it is degree. So it's an algebraic measure, but it relates very nicely with the query complexity measure that we'll be talking about. So let's move forward. So here, like we have a Boolean function where the input is an in-bit string, and we don't know the input. And our job is to find the value of the function. When you will ask the ith bit to the oracle, you will get to read the what is xi. And now we want to find the value of the output value of the function with like minimal number of queries possible. So the cost of this algorithm is maximized over all input with the best possible algorithms, that is minimized over all algorithms. So is this fine, or I can actually title we should something like that, cost of A x, where we are
You want to learn shorthand?
maximizing over x and minimizing over all possible algorithms that it creates. Okay.
You probably mentioned this when I was there, but are the queries adaptive or non-adaptive?
It's like for now, let's do. I haven't settled anything, but let's do adaptive.
Adaptive.
And here is like one example, like any algorithm we can write down in terms of decision tree. So here is a decision tree for computing the function or, where when you are querying, if you get to C1, then you know what is the output value. You really don't need to do anything else. But when you are reading 0, then you have to like keep querying. And what is the query complexity of this function? That is the depth of this tree. That is n. I have to query all the bits in the worst case scenario. So this is our model, and we'll be talking about like here is just some terminology. When the function is defined on the complete domain, that is the total Boolean function. When it is defined on a partial domain, then it is a common function, partial Boolean function, and it matters a lot. Now, to study Boolean function in the query world, there are like a lot of complexity measures which like we will not meet today. I just have listed down some of them. Like depending upon the like query model, like if you are using randomization, what kind of error you are expecting, or you are using quantum resources, we can define different complexity measures. There are some I would say this is combinatorial measures like certificate sensitivity, block sensitivity. Again, I don't need all of them, so I'm not going to define them. And there are some algebraic measures like degree, approximate degree, which we'll be talking about. Now, all of these are very old and classical measures, and a lot of other complexity measures are there. So, what are the like the fundamental problems that we want to understand here? So, you have like various complexity measures. Now, suppose you have a deterministic algorithm, you have added random resource there. Now you want to understand what is the advantage you are getting, right? So, one of the very basic problems that we will do study here, relating between two different complexity measures. If there is polynomial relation at all or not, or there is some nice example that achieves that separation between two complexity measures. That is one of the type of problem. Another is that proving lower bound or upper bound on some particular complexity measures. That is, suppose you have a quantum algorithm, you want to ask like how low your algorithm can go. So this is just very basic question that we will ask here. And the third problem that we will discuss today, it of course relates with this first two problems, and I will define them. That is composition of complexity measure. So since we'll be talking about composition, let's define composition. So here it is the goal of the composition is like you take two small function, you combine them and you create a large function or larger number of bits. It is one of the simplest way to combine function to do the composition. So I have a function f on n many bits. I take g on n different copies of g that is defined on distinct set of variables. That is the input to each g is different. The variables are different. So I get now a function at m many bits. So this is one of the very simplest way to combine functions. And for total function, like it is easy. For partial function, we just have to be sure that the functions are like inputs are consistent. That's all. So this is how we define our composition. Now we want to ask, when you combine two functions, you have started with two small functions, you have created a large function, what happened to the complexity measure? Like any complexity measures of your interest, whatever you are interested in. So precisely, the question is, suppose any complexity measure that you want to talk about. Can you express the complexity of composed function in terms of the smaller function? But here I wrote like this is a multiplication because of like we are in query world and we are talking about the complexity measure in query world, but it is also not necessarily true. For example, if you are asking this question for circuit size, then it should be plus. So depending upon what complexity measure you are like working with, these should change. And also like instead of composition, this is the most simple way we have combined function. There can be other complicated way to combine the function. I'm asking like just one of the simplest form. And to prove such thing that we will definitely need to prove some upper bound and lower bound. Now, before moving forward, so the question is why we are even interested combining function or we are interested in studying composition. So one of the like thing that we usually do to answer like many algorithmic problem or many questions, that we have a huge task, we divide the task in a smaller chunk, we solve them and combine them. But when we do that, if we don't know the complexity measure that I am working with, that behaves nicely. That is when I am combining, I will definitely get back the thing. Then there is no point of doing that. I mean, this is a very like simple tool that we use here and there. So it is like important to know how, like when I am dividing my function. By dividing, I don't mean the exact division. By dividing, I mean that when I am making a small function, when I am combining them to get back my original work, the complexity measure that I am bothered, do they actually behave nicely? So that is one of the motivation. Other motivation is that to create like a new function to prove like lower bound techniques. I mean that is one of the very like important problem here, that to prove lower bound, but in general like coming up with function on n bits is like it may be hard. But usually like what we can do, that we can start with a function on smaller number of bits, because there you can do exhaustive search and you can design whatever you want to do. Then you can combine your function again and again to get a larger function. But when you will do, like when you can do that, for example, here is a function. So here is an example. Suppose I want to create a function where degree is low and sensitivity is high. So directly coming up with such function is hard. But if I can create like there are functions, it's not I can create. There is already an example on 3-bit function where degree is 2 and sensitivity is 3. Now you can do like you can combine this function say up to the d many times. So your expectation will be like now after that degree has become 2 to the d and sensitivity has become 3 to the d. But to do this, I mean now you have created a polynomial separation, because on constant many bits you don't have a polynomial separation. But to do this, you should know how these complexity measures behave under composition, right? Otherwise, you cannot just apply this thing, just compose. So seems like it is a like very basic tool that we keep using here and there, composition. When for almost all the classical complexity measure, people do us this problem and see how they behave under composition. And we do understand that they do compose, like deterministic quantum, degree means exact degree. I will define them. They do behave nicely under composition. We also know like complexity measures like block sensitivity. They do not behave nicely under composition. We do understand them. So there is a nice survey also on that this composition problem. Except there are two big open problems that we don't understand yet how they behave under composition. One is approximity and there is randomized query complexity. Two of them are very classical, well-studied and old complexity measure, not a new complexity measure, but we don't understand how they behave under composition. So now we'll move on with like I will keep define one by one.
Sorry. So why does block sensitivity not
Compose. So we can think of a function, say, let's take try. So and the first,
Yeah.
both of them are full and block sensitivity will be square root 2.
Yeah.
They do not compose. But we also can do that. I mean, block sensitivity should be then full, right? If they do compose nicely, but it is not.
Okay, because I thought like now we know that like measures like degree and block sensitivity are essentially the same up to polylog.
Up to polylog, yeah.
Oh, that's important.
Yeah, that's very important, yeah.
Like when you say they do not compose, you mean that there is some task instances for which.
Yeah, it fails, yeah. For all function, it like generally do not compose. But there is some function for which it fails, but
There is some function for which it fails.
yeah, like tries. Yeah.
People studying like.
Here by composition, you're meaning that the measures multiply.
Multiply, yeah.
Right, okay.
I mean, for example, even block sensitivity under certain condition can compose. That also we can prove. That if these things happen, they will compose. That is, but in general, it is not true. That we know. That we understand.
Sorry, and when we say that it fails, I mean, because once we put a theta, there are two things. There is an upper bound and a lower bound. It basically means that like the up, yeah. So I mean, you need the lower bound.
Lower bound.
So
I mean, in the sense that the the upper bound also
fails, yeah.
in the sense that the measure of get
upper
numbers
bound can be really large.
could
Sorry,
potentially
yeah.
be much larger than the product of those. I mean, it depends on what the measure is.
Okay, fine.
I mean, but for most reasonable things, I would think that the upper bound is like a trivial upper bound.
Right.
Oh, right.
Which is a
Sorry,
question
I
of, yeah.
The upper bound is
Yeah. I mean, can be very large. I mean, yeah.
Yeah, okay.
I mean, like, so what you're saying about block sensitivity, is it also like input dependent? Like if a block sensitivity function, is it the case that for any inputs, this will not hold? Like, does that make sense at all?
No, these measures are maximized over normal.
I mean, all the complexity measures, that is worst case scenario, that is for the function maximize over all.
I see. But like, is there an average case question over here as well? I'm just wondering.
Yeah, there are like average sensitivity defined and studied.
Which is
I mean, that those are a bit different complexity measures. Also, ER.
So when you say approximate degree, is it like you take the polynomial?
The Boolean function, I will
So but approximating in the sense that after a threshold or no, like it has to approximate point.
I
It's
see.
block issue point.
Yeah.
It's block issue.
Yeah. Okay, so now I will define the first problem. So before going to the approximate degree, just like let's see what is exact degree. Exact degree is just the polynomial that represent our Boolean function exactly. So this is a unique multivariate. Now, instead of representing a function exactly, that is the polynomial should output 0 and 1. What if we demand that your polynomial output some like when the function was outputting 0, your polynomial output something close to the 0, like 1/3 interval of 0, and when my function was outputting 1, then my polynomial should output again the 1/3 interval of 1. So it's not again the exact representation. I'm doing approximation here. So just one thing to note that I have used like 1/3 just to standardize this thing, we can actually define like external approximate degree, where external is like non-trivial, that is not half, strictly dependent. Less than half, sorry. It's fine.
Would it make sense to also approximate the for all condition that if it's
For all?
close enough for most x and zero to the end?
Sorry, can you?
So I'm wondering if it makes sense to approximate the setting condition also, that the polynomial is only closed for most values of x on the hypercube versus on all.
Not all points.
Yeah.
That will give the
It has been-
other kind of
It
complexity.
has been looked at.
Yeah, I mean, that will give you like other
Probabilistic approximately.
Yeah.
And I mean, what you're looking at is the dual of that, which is distributional approximation.
Distribution, yeah.
Both have been looked at.
But yeah, so all the complexities that I wrote here listed on those actually, you have to have for all inputs on the whole level.
Since P of x has to be in 0 or 1 or but that's not true.
No. It is a real.
Slightly, see, one or could slightly be below zero.
Yeah. So the immediate question is that like when we are not trying to exactly represent the function, are we getting some advantage? Here advantage means advantage of degree. Am I saving on degree? Not like here is an example where we are actually saving on degree. So for all degree is full, but approximate degree is square root 10. So we were saving a lot on degree. But there are functions for which we will not save. For example, if you take majority, degree and approximate degree both will be full. But there are like a lot of cases where we will save on the degree. And is the same function, I'm just listing down because I will use that. So both of them for n bit or n bit and approximate degree is square root.
This is the root n of around easy polynomial.
It is only, I mean, the saying is that the gun has only one bullet and the bullet is called the Chebyshev polynomial.
Or like other way I think like that there is Grover's search and quantum is upper bound and approximate degree. So or I'm searching for one.
Classical
Oh.
person.
Okay. Good word then yes, then fine. Okay.
But it's Chebyshev, like product of like so.
No, it's Chebyshev, but you do some scaling and turn it around.
No, that's fine, but like that's for one. Using let's say to for you
Which is
to
the
multiply.
Yeah, so you just
Yeah,
add the.
Yeah, you go symmetrize and then there is a single Chebyshev.
Yeah, see it very.
Sometimes people can't figure it out.
So Akhtar was doing this in his last query complexity lecture.
I mean, which means where I added and again, like same function.
To remind
No, not making it, but it will remind.
Okay, I see. So the point is that you take the sum and then you would want to distinguish between
Yeah.
0 and 1 by n, and
Yeah.
because Chebyshev polynomial has 1 by root n type behavior at the edge. That
You did that in your real stable.
like it is
You did the
edge behavior at it. So that edge behavior is what we use.
Yeah.
Yes.
Okay, so here is like some of the applications which I like. I don't know all of them, but like upper bound and approximate degree gives upper bound and circuit complexity that is useful. We use a lot for Oracle separations, like in AC0 statistics and all, in communication complexity, and of course the important part that I care about is it gives lower bound and quantum query complexity. So there are like a lot of applications of approximate degree. So just this slide is just to show it is a very useful quantity.
Sorry, so for approximate degree, what is known? Like, known we find approximate degree of F composed with G is at most the product.
Yeah.
Okay,
That
that
is
is known.
the-
Oh, I see.
Then
Okay.
so there is a nice survey by Bananthelas and yeah, there is.
That's not trivial.
No, I don't see it immediately.
No, it's not.
Oh,
Exactly that.
okay.
On this login thing, you can get.
I see.
So I have here, like let's see.
Okay.
So to prove composition, we have to go through lower bound and upper bound. So let's try to do the upper bound first, like you asked. So what is the live approach to do upper bound? I will take an approximating polynomial for A and an approximating polynomial for G and try to compose them, right? Now, what is the problem here? So
The input to F is not Boolean.
Boolean, so we will fail.
Guaranteed.
Yeah, we will fail. So now the problem is that now we don't know how they behave, so in the domain is not Boolean, right? So that's the problem we are facing. Now, okay. So since we have polynomial, so here is a very like beautiful technique that Sestov did to make polynomial on discrete domain robust to the noise. That is, so suppose I have a polynomial on this discrete domain. Now I'm coming up with another polynomial P robust. That is, so if there is error to the domain, that is if around every point, suppose I have 0. So there are now I am considering some open neighborhood around my point, and now my polynomial can handle all those noise, but still can approximate nicely. That is from the original polynomial, the value is like delta curve. And how much I am harming on the degree? It's just an additive error, like plus log of 1 by delta. So like really is, they don't care, like that's a constant. So this is a okay. So once we have this, then we have the upper bound. That's fine. The another reason that let's keep in mind that to prove the upper bound, we needed this idea of robustness. That is, when I am composing two functions, there is some error taking place in between, and I should somehow come up with some handle to manage those errors. So my robust polynomial is doing that for me, right? I mean the error that I am inducing in the domain, it can handle that. So that's my robust polynomial is doing. Now with Sestrov's technique, upper bound is done because for the outer function you just make the robust polynomial and you compose. And the open problem is the lower bound that we want to. And here there is again some fact. I'm not going to define all those complexity measures, but like someone you noted down that there is like polynomial relationship between complexity measures. Like here we have complexity measure that is sitting in the upper bound and lower bound of approximate degree, and we know for like many years that they compose nicely, but we don't know for this complexity measure approximate degree.
So I'm a little lost. What is lambda and Q with you?
So I actually haven't defined. There's some like other complexity measure that gives lower bound or approximate degree. Let's leave it for now. Upper bound is exact degree.
This is a very recent result. The approximate degree is lower bounded by.
Lambda is very recent, but the quantum and degree we knew like a lot.
Yeah.
So just to, I mean, I don't know what Q and lambda, but presume this basically to say that there is a complexity measure that is always smaller than approximate degree, which composes. And there are complexity measures that are always larger than approximate degree, which also composes. Nice.
Compositions don't have sandwich.
Don't have this theorem also, yeah. Yeah.
Okay. Can you just go back to your previous slide? You went from 09 to 13.
Sorry.
There was a different paper which used this and kind of proved the.
So the next slide. Yeah, it's an 80-page paper.
No, so the artificial defined robust performance is not on the same paper where he proved the upper bound. In the early days, you had to like typeset by hand.
Maybe
No,
it's
no,
just
same. I think I just wrote the channel person. Sorry.
It was submitted with POC.
I did this mistake. Yeah. Okay.
Talked about polynomial times.
And here, like this again, we will use in like some of the proof technique, which is very like how to prove lower bound and approximate degree. So this approximating polynomial is basically a like optimization problem, right? So this is my primary. So I want to minimize the error, and I have a polynomial where I have to decide like the coefficient of my polynomial and such that it behaves like this, right? For all the point in the domain. And so I want my polynomial to be like degree strictly less than D. So this is the primal. For the dual, I wrote here that is okay, that you have to, message the dual to get into that form. Of course, that is not the direct dual because here I have 2 into 2 to the n many constants. So because of this mod. So here like I can take some, psi 1x and psi 2x both just to interpret this like exactly in the forms of dual. But after some messaging, we can actually land up here where I have to figure out some function again, psi x, that is the dual polynomial such that it is like the second term is fine, but the third not fine, second term of course we will get from this primal, but what is the third term is saying your dual is a purely high degree, that is in your dual polynomial you don't have smaller degree polynomial, that is the like capturing the like idea of the primal.
Sorry, what are the variables here? The variables are the coefficients of T.
Coefficients of
I see. Okay.
And why is psi a polynomial? I don't get that.
Well, psi is a value that you
Size
assign
and
to a
value,
matrix.
it's like I mean here for this 2 into 2 to the many constant I will take the dual variable, right? So I just like took all the dual variable together to represent psi. Just that's it, like that's why I said I mean it's not the
2 to the n unknown.
2 to the n.
So what are you calling the dual polynomial? What is that?
So psi actually when we write down that will
I mean,
come
it's a real value
real
function.
function
It's
which is
not a Boolean cube, so it is another
multilinear
polynomial. It is a polynomial.
I'm going to take 4 years and say that it supported in the last year. Because of this.
so after actually we have our this, I mean that's why I said like it's not directly the dual of this thing. We have to message at some level to get this right. So by like this is basically giving you a characterization to prove the lower bound, right? So we can like now claim that so degree is greater than equal to D if there is some size that satisfies all of these conditions just by which.
So the third condition, it might be sort of useful to say it in the way this, right? I mean, you only look at, instead of looking at all polynomials P, you are looking at just the monomials, right?
Right.
And therefore
Right.
psi has no monomial, the Fourier coefficients of psi below degree D are 0.
Right.
That's all it's,
Right.
that's generalized.
I'm just writing this down because this will be helpful for us. So science, like you said, let me write down now this way. This is 0 for all is strictly less than D. So I can do in monomial level also. We are actually doing in monomial level because when I'm writing from here, this is a D degree polynomial, so I don't have the other variables here. Yeah. Okay. So let's move forward. So what, like before going into the proof technique, there let's see what some of the known results. So system again have proved that using the dual only. So the another thing is that this lower bounding technique mostly goes by dual, whatever we like have here. When the outer function has full approximate degree, then we know the function composes, and this proofs goes by this dual composition technique. But the problem is, even with this theorem, we cannot solve for some like easy function like all of n, the simple function.
So f is the function that has n variables in it.
Yeah.
And we are assuming that the approximate degree for f is like close to 3. Okay, in which case,
You
up
can-
to some log factor, you are like the tilde probably.
Yeah, yeah, yeah.
Okay. Yeah, not the white tilde.
Yeah, sorry, we should have used that also, yeah. But using that theorem, we can solve for all of n, right? But or random or like because I don't have full approximate degree. So even this for the simple function, it was open for quite a long time. And after this many work, it finally was resolved that this low bound for approximate degree of all of n is like really tight. And like, okay, this proof again, like all at least this test of one and all of these proof techniques goes by a dual composition. So you take the dual of two functions f and g and try to compose them. And after that, there was a big jump where we actually people have managed to replace like, oh, okay, when you have like all of and you like ask like if we can replace any of them, by any general function. And of course, like yes, we were able to show that when the inner function is like g, like any g, but the outer function is odd, then approximately decomposes. But again, here the problem is that this proof goes by very nice quantum technique, but we don't know if there exists a dual polynomial proof for this thing, that is dual composition proof for this thing. Which is why like also this proof technique cannot be extended to the other function. It is like it is built up for all function.
And this proof gives us a quantum technique.
Quantum, yeah.
It has to somehow, there's no classical analog.
No, there is no class. I mean, that is the open problem when written by them also, that like just come up with a dual composition proof, because dual composition proofs are view in the general open problem, that where we are, how much progress we are making. This like we know the lower bound, but we don't know where we are right now after this also.
So by the composition guessing, we don't know how the proof which goes along the lines of get a certificate for a dual certificate for the OR, dual certificate for and get out of it a dual certificate for the compose. The proof doesn't go along these lines. It goes.
It's completely goes by like quantum algorithm and upper bounding technique, and you will end up proving for all. Like it's not like, I mean, what is the gist of what? Gist of what is like there is a 0 and 1 layer, right? Like you proved in the class. So you will end up proving for those functions if you try to generalize those. And when we have all, like we definitely expect if we can prove when the outer function is like symmetric, and that they actually have extended this proof of all when the outer function is symmetric. So this much we know here. Okay. Now let's move to our results. So again, so after that we will also not able to extend that very much. So we just using that OR proof, we asked like all of the proofs that goes for symmetric functions, because we are working with and OR and symmetric functions and all. Can we break the symmetry? And in that term, like this again, so we're in a very complexity class, like using Nissan-Segeti kind of technique. And of course, some in approximate degree genre again, like we can deal with partial function, but you have to do a different proof. It's not like the total function proof will go for partial function. So we were able to show that the square root of block sensitivity, lower bound is square root of block sensitivity and approximate degree of G. Now there is two things, like this thing is giving lower bound for any Boolean function, but like that the lower bound should look like something approximate degree to the 1/4 into approximate degree of G. That is for the outer function, the lower bound is like 1/4 if we replace block sensitivity by approximate degree. And it also gives the composition theorem for all functions for which approximate degree is square root block sensitivity.
So, I mean, isn't it good to say it this way? If the composition theorem that you are trying to prove is true, then this better be true.
Right.
And
This
you are
has to be
just-
true.
And you are corroborating that.
Right. This has to be correct. Yeah. I mean, this is the like much weaker bound that we are
Could be
expecting.
much weaker, yeah.
I mean, of course, much weaker. I mean, there are examples. This is
Sure.
like this. Yes. And what we are expecting to get the like original bound. And but the square root block sensitivity, this square root cannot be improved. What can be done in this thread, that replacing these complexity measures by some other complexity measure and trying to prove for some other classes of functions, because as long as you come up with new complexity measure, you are proving composition theorem on the new classes of functions. That can be done. Okay. This is one of the results, and this is another result which I will try to give a proof idea today. That is again, so we have tried to use this dual composition technique and see that where we can actually land ourselves just using like simple dual composition. And we were able to prove composition theorem when the outer function is some recursive function and outer function is some recursive function and inner function can be anything. So by recursive function I mean that like you have like some small function, say majority on 3 bits, then I am doing majority on 3 bits, majority on 3 bits and majority on 3 bits, and I will keep doing that, say d times. So this is like I will keep recursing. And why this is like when you have some composition theorem for some class, you really like directly cannot expect to apply that theorem recursively to get a composition theorem for recursive function. Why? Suppose in your lower bound you have some constant or something hanging around. Now when you are actually applying composition theorem recursively, then you are like gathering that constant also, like say to the d times. So that is like actually costing you a lot in the lower bound. You are not getting a good lower bound. So when we are talking about recursive function, we should better be get out a good bound without applying recursively the same composition theorem. And when the inner function is recursive function and outer function can be anything except and or that we don't have, because that is again another like big open problem in this area.
Inner function terminated.
Sorry.
The outer function terminating and the inner function.
Yeah. Because like when the what do we mean by recursive or? Recursive or will give you a big or just nothing more. Similarly, recursive and will give you a big and. So here like is like another open problem which we don't know. Like the previously we saw that people have solved when the inner function is or, but we outer function is or, but we don't know if this is true. That when the inner function is or, that is again a like big open problem. Maybe a like big jump to solving towards the main. So this is open when the inner function is or and.
So there are other functions h such that h power d is just a larger h, right? Like for example, if it's parity or something.
Yes.
What happens in such situation?
For parity we will have this.
Sorry?
For parity we have this.
Where is the parity?
No. I'm just saying that if the maybe I misunderstood it. I thought the objection for or and and was the fact that if you had a recursive or a recursive and, you're basically doing or and.
Or
Like it's just larger.
Right.
But that also holds for other functions like parity. So I was just wondering, like.
For parity we have.
Okay.
Because for parity in general also it is known. So when the outer function is parity.
No, G is the inner function.
I'm saying when the outer function is parity, then we know. When the inner function is parity, then also we know. It's known for like long.
Oh, the outer function is parity is known because the approximate is full.
And inner function.
More general,
Right.
approximate is
Right.
full.
And inner function is parity, that also you know because parity is sine degree is full.
Oh, right.
And you can prove from there.
But these are not ad hoc techniques, right? They're not, each one is sort of using one.
Sorry?
I'm just trying to understand. So each of these cases, there's a lot of cases.
Lot of cases.
And each of these cases being handled by some ad hoc technique, right?
Not really. I think I will just prove for recursive majority, and from there, just little bit of case study, but they will be done. That is one proof after that. Main proof is like proving for recursive majority or recursive and.
No, so your result will unify everything, is that what you're
Yeah.
saying? Oh, I see.
That is the main proof that proving for recursive majority and recursive AND or tree. They just trying to use that like when I have this function with constant arity, I can embed function there. It's not a lot of number of cases. It's not just not that. But yeah, there will be some cases. That is also true because I will keep out monotone and non-monotone cases differently and all. Yeah. Okay. So this is like step 1, and this can be done in a various way. I will try to give a proof idea of this in a bit. So what this is saying that when I'm adding a small gadget here in between two functions where majority is the gadget and majority is the log n many bits, that is the arity of the outer function. Just by this, So really have very good, nice lower bound that you wanted to see. Like approximate degree of R, approximate degree of G. And that just we can like land up here if we do just the this simple dual composition technique that we were trying to do.
Sorry, what happened to what your result is?
What happened to the?
What happened to this majority of? Oh,
I could not take out this majority, which is why here you have a log n loss.
no, okay, there's a log in loss, right?
Yeah, sure. But like still we don't care because it's log n. We are ready to lose log n, right? And so this can be proved in a various way, like really,
You can, if you press the red button, the board just moves to. You don't need to edit.
Oh, that's cool. So I'm just trying to give a proof overview of this lemma because I want to conclude what we can problem from here. That is, so when we are trying to solve this type of composition question, what is the usual approach? So given an approximating polynomial, for f compose G, say this P is given to me. My goal is to come up with approximating polynomial for it, like any one of the small function, like we want to do. So we are given the algorithm for the bigger function and we want to do for smaller functions. Say I have made some polynomial things. Now when we'll be happy, like we did a good job to do that. If we actually have proved that, whatever the smaller thing that I created here, this degree of Q is upper bounded by degree of P by approximate degree of G. So basically this is approximate degree of F compose G by approximate degree of G. And this is approximating polynomial for F. So we are happy if we can do that, right? Now the question is how we can do that. So this is our goal. This is what we'll be happy if we can get. Let's take like there can be various techniques. I'm trying to describe one of them. Let's take an operator, linear operator, say L, that takes function that is on Mn domain to some function that is on Mn string domain. So I'm just killing the in part here. And how will you do that? This is again a very generic technique. Arrange the image of this thing is the basically image of this operator is defined on an in string. So say I'm choosing point some distribution. I'll write this down. Where this mu Zi are basically some distribution that I will be defining over 0 1 to the m. So if I had this distribution, then this mapping is fine, right? This operator is fine because here I have like n-bit string that is the image, I am choosing each of these x1 is basically denoting a m big string because I choose point from this distribution and my h is defined on any big string. So we are finding this. Now how we are defining this distribution with the fact that we want to do that and we want to like satisfy some other properties. Okay, so okay, so dual is very high now. So what I wanted to do that. I mean, I cannot just choose any distribution. We can change the distribution, but here is the very easy way to get the distribution because what really I am doing, I am killing the point for g, right? Killing the like monomials for g, like inner function. So I want to choose a distribution that is coming from the dual for g. So
We have a stick there.
sorry.
There is a stick for the dual.
She also has a laser pointer if needed.
Yeah. I have a laser. Okay, so if like okay, there is every day. I should have wrote G here, but like this is true for like any when I have an approximating polynomial, I can like get a dual from like derive a dual from there, right? So suppose like psi is the dual for G. I'm just also making a little bit of 2 in here. I'm taking 1 by 2 epsilon approximate degree of G. So if epsilon was like a small constant, this is also fine, right? 1 minus epsilon by 2. Fine. So suppose psi is the dual for the function G. What is mu? Mu is really this thing, and mu 0 and mu 1 are index distribution over the domain, whereas mu 0 is just the negative part and mu 1 is the positive part. Now we'll need some of the properties of the distribution, but I mean this is the way to define the distribution and this is fine so far, right? Now here is I am going to make some claims which I will skip for now. That is, if we are defining the distribution in this way, first claim is that you really have made the this degree criteria that you were happy to meet, like you wanted to meet. That criteria have been made. That we can prove that I am skipping for now. So this I'm just keeping that part here that we are we have we are able to make this part because distribution is a nice dual is a nice thing and that helped us to do that. That is claim 1 and claim 2 is that when I am choosing point, expectation of mu 0 of gx, this is less than epsilon and I don't think that will be a problem for now. So this is the claim 2 that distribution has certain property that coming from the dual that we can prove that when I am choosing the distribution for mu 0, then the expectation lies between these. And when I am choosing the point from mu 1, then the expectation lies between these. Now, once I have this, then what really I do have, like the
mu 0 is supported on 0 to G and mu.
correct. So I am just like if we just put the whole thing here. So here it was just an expectation. So it is a linear operator. So this LH Z1 to Z10, this is nothing but like f of expectation of G where x1 is chosen from mu Z1 and looks like this, right? Now the question is like, there are certain things like f was a multilinear polynomial, which is why I am able to take the expectation inside. In general, we can't do that. So, okay, after this thing, what I am really getting here that I got some, Z1 dash to Zn dash such that they are really close to Z, but they like there, this Z1 minus Z1 dash that is less than epsilon. But we don't know A is not Boolean, that we don't know. So we are lost on that part, right? So like so far it was going good, but we cannot really do that after that. I mean, we don't know now how it is. Now to manage this thing, I would say like it's not a good fix, the bad fix, but it's an easy fix that we can just use majority. That is, I am using a logarithmic majority in between. That is like in this function, instead of just working with f compose g, what you can do that you can. I mean, here clearly we are lost due to this noise that we cannot handle, which system could handle, but here you cannot handle. So the easy fix is that so you take the majority on log n many bits. Now sample from the same distribution log n many times. That is the same mu 0 on log n many times. Then you are actually able to reduce your error. So, like whatever epsilon I am getting here, the distance, now I have managed to reduce it like epsilon to the n. And now my polynomial can actually handle these things. So this is the I would say like basic intuition of this proof, which also says that the dual that we are working with, that the dual for usual approximating polynomial, that may not be sufficient to attack the problem for all functions. We may need to come up with the dual for robust polynomial. I mean, because the robustness was very useful, that came into the picture and we really cannot handle it. I mean, we cannot, of course, use the Chekhov's robust polynomial here because that is not multilinear, so you cannot do that. So, what is the dual for robust polynomial and how we can deal with it? That is one of the takeaway of this thing.
So the dual, that's why, if the dual polynomial, in the robust polynomial, I know it's not multilinear, but that's the only bottleneck, right? In the sense that suppose you knew that every polynomial f, approximating polynomial f, could be robust if I keeping multilinearity.
Then you are done.
Then you are done. Right?
Yeah, but also you cannot use extra variables. Usually the robustification that we do, if you want to keep multilinear, you will end up using extra variable. That also like in our case also we end up using extra variable. Because in general, what this should look like in polynomial world, this is a single variable polynomial. This majority we are not really using the log n many bits in the polynomial world. When I am trying to error reduction, I am just using a polynomial, single variable polynomial for majority, right? Well, not the multilinear one. But here, like that is not the case, which is why majority hanging in between these things. Okay.
Is it known that for the Chekhov's robustification we need multilinear, non-multilinearity, or it's conceivable that?
It's not multilinear.
No, but is it conceivable that there is a robust polynomial which is fully multilinear?
I think it can be proved that with the degree bound, like you are not losing degree much, you cannot do that.
There's an example.
Yeah.
Okay.
I think that is given implicit in system of some of the work, like implicitly written, like because usually if you just ready to do one by epsilon kind of thing, you can actually end up getting robust. Just like I'm saying the multiplicative error, not the additive error. If you are ready to lose this much error, you will end up getting something, right? But I mean, it's not. At least I would say it's not explicit. It's not there. But yeah, this is the problem. I mean that's the point I'm trying to make. That this is the problem. This robustness is the problem, and this is just a simple technique. Like they didn't do anything fancy. Yeah. And okay, so yeah, now clearly we are stuck here, and if we for some function, for some classes of function, we are able to show that the decompose G is upper bounded, I mean lower bounded by this F compose majority compose G with this log like log and laws in between, like we are ready to lose now. Then we can prove composition theorem for such classes of functions, and we show that this holds for recursive function. And the technique is again very simple, that there is a classical result where like Valiant, and of course later going to prove this again, that this majority logging is a sub function of recursive majority on recursion log logging. That is usually for majority n, the recursion should be logging. So we are using majority of log n in between. So we can embed this function in log logging tree, like log logging tips tree. So which is why what you can do that when you have majority, you can now use the outer function being recursive majority or the inner function being recursive majority, like any one of them. Say here I am doing the outer function being recursive majority. If the outer function is recursive majority, and I have replaced embedded this majority in a larger function. So this is much harder function. I can do that because I am now working on upper bound. I can just keep replacing by the hard function. There is no harm. And now I can actually take them together and ready to lose something and prove composition theorem for recursive majority being the outer function, right? We can similarly do for the inner function also. There's no problem there because we again just do the clubbing and we are ready to lose this log logging, so it's fine. I'm almost out of time, and similarly this like Valiant again proved that you can actually embed majority in and your tree also. That is again the length is log logging. So let's just a similar technique. You can prove the composition theorem for log logging. After that, for any recursive function, what we really did that, like you mentioned, we did the case study, like where you can embed these end of all tree, and I'm skipping for these for now. I'm just giving one small example. So this is one of the like hard case. Suppose you have a non-monotone function and you have an OR there embedded. Now you cannot ensure that there you can really embed AND. If there is OR, there like may not be AND there, right? Like how you will do that? You will just do the this De Morgan thing because you are on a non-monotone case. So there is some input where you are changing 0 to 1 and the output getting changed from 1 to 0. That is the opposite is happening. And that is actually giving you the this for example here if I am putting x here, I am getting the negation of x. So that is how you create the negation. Once you have the negation, you can apply the De Morgan. So it's not like in one edge you are embedding and now. This is a three length tree where you are embedding I. So there is some loss in the length also. That is previously we were working with say length L. Now you will need some length like 3L kind of thing. But still we are like fine because this is constant. So this is the theorem we have, and I will just quickly go over this open problem because it's almost ended. So the query we have defined. So in randomized model, you have just randomized access in the decision tree, and you expect you have the random point losses in the decision tree, and you expect your algorithm to give correct output with probability 2/3. That is the complexity for which the problem is open. That if randomized query complexity composes or not. And here, of course, the question again have two parts, and the upper bound is there, and the lower bound is the double problem that want to solve it. And there are various again study here, and the flavor of the result that we are talking in approximate degree, that inducing some other complexity measures and proving composition theorem, that has been done here. And here just I made this noisy a different color because our result just better analysis of these result, and using which sorry.
That is sort of right? GLSS. And that you can replace that chi g by square root of.
Square root of right. I mean that is a complexity method they introduced, but I just didn't that it's not easy. Yeah. I mean there are a lot of implications of these results which I haven't. I am skipping this also for now. So what is our problem here? So for approximate degree, we have seen that such result is known when the outer function has full approximate degree. Can we prove the similar kind of thing for it? And this is our result. We proved that when the randomized query complexity computes, when the outer function has full randomized query complexity. But I would say like this is not giving a better intuition. This is just an analysis of this noisy algorithm that the result that I displayed here. This noisy like algorithm, whatever they did here, just a analysis of that. So okay, and what are the applications of this thing? What we did, like our goal was trying to break the symmetry, but we could not. So we just proved for Punto symmetric function, where the symmetric part is non-trivial. That is, it depends on the Hamilton of the input. Some composition theorem for that. And this is the table. Of course, the main open problem is still open. And here is some maybe weaker problem that when the outer function is transitive, can you prove that? And of course, these I already have mentioned. Can you prove all compose G using dual composition method? And that's all.
Questions?
Simple way. How do approximate degree and randomized query complexity
Related.
what's the relation? We haven't seen.
There are polynomial relation,
Yeah.
like you said, but are you asking like directly like intuitive relation or like?
No. Just
The
what's the polynomial relation?
So what's the polynomial relation? I think R is then approximate degree to the 4 if I'm not saying it wrong. And there is example for which it's also like the separation is also. I mean directly the actually composition problem is completely different. It's like
Yeah.
like not on the same page at all.
More questions? That's standard.